This is just, again, going to be a quick walkthrough of the sum and difference formulas lesson. There's 3 different sum and difference formulas, obviously one for sine, cosine, and tangent. Sine is the sine of alpha plus or minus beta is equal to the sine of alpha times the cosine of beta, either plus or minus cosine of alpha times sine of beta. So sine of the first, cosine of the second, same sign, cosine of the first, sine of the second. And really, it's after that point, it's just utilizing the hand trick or your formula chart to be able to reduce these things down. So if we look at this first example, well, first of all, sine of 105 is in quadrant 1, and we want things to be in quadrant 2, so we're going to, I said that backwards. Sine of 105 is in quadrant 2, we want things to be in quadrant 1, so we use the reference angle for 105 degrees, which is 75 degrees. In the second quadrant, sine is still positive, so we don't have to distribute a negative. Now we can make 75 if we add 30 plus 45, right? 30 plus 45 is 75. So we can take 30 plus 45 and then use the sum formula to find this exact value without having to use a calculator. Sine of 30 degrees times cosine of 45 degrees plus cosine of 30 sine of 45. Well, the sine of 30 is a half, the cosine of 45 is square root of 2 over 2, cosine of 30 is square root of 3 over 2, sine of 45 is square root of 2 over 2. You multiply fractions by doing top times top, bottom times bottom, top times top, bottom times bottom. And we can add fractions if they have the same denominator, which these do. So square root of 2 plus square root of 6 all over 4. Yes, you could have given me a decimal approximation for this, but if we pretend like we don't have calculators anymore, this is the exact value for sine of 105. We can also find the sine of 17 pi over 12 using, again, reference angles and then the sum and difference formula. Now 17 pi over 12 is in quadrant 3, so to put it back in quadrant 1, its reference angle is 5 pi over 12. But in quadrant 3, sine is negative, so we're going to have to make sure we have a negative in front of this reference version of sine, and keep that negative floating down all the way to the very end, so that we are taking into account it's in the third quadrant. Now I can make 5 pi over 12 by adding 2 pi over 12 and 3 pi over 12. 2 pi over 12 is pi over 6, that's like 30 degrees. And 3 pi over 12 is pi over 4, which is like 45 degrees. And so I can still use that sum formula for sine with these angles instead, and their exact values, multiplying them together, adding them together, and distributing this -1 to find that the exact value of sine of 17 pi over 12 is negative square root of 2 minus square root of 6 all over 4. That's the sum of sines formula. Now cosine is a little bit different. A couple things to notice about cosine. First of all, the cosines are together instead of separated like they were in the sines. And I wrote these specifically opposite on purpose. If you're adding, like having the sum of cosines, sum of angles, you're actually subtracting these values. And if you're subtracting cosine, you'll actually be adding. So make sure you notice that those are opposites. You can kind of look through these examples. They work pretty much exactly the same. Make sure you're looking in quadrant 1 and take the reference angle into account. Cosine is negative in quadrant 2, so we need to have a negative in the very front. And then we can just create 15 degrees by doing 45 minus 30. Yes, you can still do 60 minus 45. Both would get you the same answer. If you do the cosine of 1 pi over 12, okay, a way to make 1 pi over 12, which first of all is in the first quadrant, so we don't have to move it around, is 4 pi over 12 minus 3 pi over 12. There's multiple ways to do this, but this is the way I just decided to do here. So it's cosine of pi over 3 minus pi over 4. So if we fill out the cosine, the difference of cosines formula, take their exact values, multiply, and then combine like terms, because we can add those fractions, we get square root of 2 plus 6, square root of 2 plus square root of 6 all over 4. The last formula we're going to have, and we needed to add this one to our formula chart, is the sum and difference of tangent. Now the one that was originally on your formula chart is actually just the sum of sines over the sum of cosines, which makes sense because tangent is sine over cosines, but we can actually derive a different formula that's a bit easier to use, and it's an identity here that we can add to the formula chart. Tangent of the first angle plus or minus tangent of the second angle all over 1 minus or plus, opposite, tangent of the first, tangent of the second. So if we look at this example here, we're doing the tangent of 15 degrees, which is in quadrant 1. We don't have to move anything around. We can do tangent of 60 minus 45. Yes, you could do 45 minus 30, but we're going to want to try to avoid using tangent of 30s because tangent of 30 is square root of 3 over 3, and putting fractions inside of fractions just stresses you out. So if you can make your angle measurement out of some 60 degrees instead of 30s, go for that. Again, it would get you the same answer, just I know it will freak you out. Tangent of 60 minus tangent of 45. Remember, these signs match. This sign is the opposite. 1 plus tangent of 60, tangent of 45. I've only used the formula so far. And then I just take those exact values. Tangent of 60 is pi over 3. What? Tangent of 60 is square root of 3. Tangent of 45 is 1. And you have 1 plus square root of 3 times 1, which is just square root of 3 minus 1, all over 1 plus square root of 3. Now, just to prove that this was true, if you got the exact value there, it'd be 0.268-ish. And if we had used 45 minus 30, when we would reduce that down, we'd get 1 minus square root of 3 over 3 all over 1 plus square root of 3 over 3, and like, yiza. This is the same exact value. Additionally, if you're looking at the answers in the back of the textbook rationalizes the denominator, which really we should be doing, but I'm not going to have you do that. So if you just want to stop when you get to an answer that looks like this for a tangent and then check its exact value versus what's in the back of the book to make sure you have the same exact value, that works for me. Otherwise, you have to multiply by the conjugate here, and it's a whole big deal. Now, a couple more things we can do with these sum and difference formulas is kind of work backwards. So you need to ask yourself the following questions. Which formula is it using and which sign? Because we look at this one, and sine and cosine are paired together in this first term, we know that this is a sum and difference of sine. And because this is a plus sign, we know we're doing a sum of these angles. So we're just actually doing the sine of 25 plus 35, which 25 plus 35 is 60, and the sine of 60 is square root of 3 over 2. So voila, I've gotten the exact value. Same thing happening over here. Because the cosines are together in the first term, we know this is the sum or difference of cosine. And since I'm subtracting in the formula, I know it's the opposite for cosine, so this is an adding, a sum. So we're going to do the cosine of 20 plus 10, that's the cosine of 30, and guess what? Cosine of 30 is square root of 3 over 2 again. So we can work backwards in these formulas. Here's a few more examples in radians, perhaps. This one's kind of interesting. So we know that this is sine because the sine and cosine are together in the first term, and we're subtracting. Okay, well, I can't subtract these fractions until they have a common denominator. So, boom, I've made them have a common denominator. 3 pi over 12 minus 11 pi over 12. Well, that's negative 8 pi over 12. Now, we can reduce this fraction because 8 pi over 12 reduces to negative 2 pi over 3, which we just want to work in reduced fractions. And because sine is odd, there's a property of odd functions that if you put a negative input, it just makes the entire function negative. We learned about this in like November when we talked about odd and even functions. It's also on your formula chart. Your formula chart on the odd and even identities, it's going to say sine of negative theta equal to negative sine of theta. So we've just used that identity right there. Well, 2 pi over 3 is in quadrant 1. So if I want that to, in quadrant 2, what am I saying? If we want that to be in quadrant 1, we just look at its reference angle. 2 pi over 3's reference angle is 1 pi over 3. And in the second quadrant, sine is positive, so I don't have to change this sign. It's already negative from the odd and even thing. I didn't have to like do another negative or anything. Well, the sine of pi over 3 is just square root of 3 over 2, and we're just going to make that negative since we have this negative from the odd and even identity. Sometimes you have to be a little creative. The last one, pretty obviously this is tangent. That's the formula we're using. And since the top is positive, we know we're adding. So this is going to be the tangent of 30. And the tangent of 30 is square root of 3 over 3. All right, last but not least, we're going to help establish this identity. So remember, establishing an identity, you have to follow some of the identity or formula rules you know, and I like giving a reason why each time. So if we look at this first little bit, we have the sum of sines. So I use the sum of sines formula. Sine of alpha plus sine of alpha cosine of beta plus cosine of alpha sine of beta. The second thing I have is the difference of sines. So I'm going to use that formula. Sine of alpha cosine of beta minus cosine of alpha sine of beta. Well, now I have a positive and negative cosine alpha sine beta, so those are going to cancel. And if I notice now that these are the exact same terms, so I'm just going to add them together. I'm going to combine like terms, simplify, to get 2 sine of alpha cosine of beta, which is what we wanted to prove or establish the identity. QED.